So next factor which influencing the organic reaction is hyperconjugation. Now, what is hyperconjugation? So let's take an example. Suppose we have an alkene, CH2 double bond CH and CH3. Now, there is no conjugation as we can see. There is no case of conjugation, the 6 cases we have done. So technically, there is no conjugation in this case. But what if I break one bond of carbon like this, CH2 double bond CH and C, H plus H and H. Now we can see the conjugation pi, sigma, and negative charge. We have broken the one bond temporary, so carbon has negative charge and hydrogen has positive charge. Now, is there conjugation possible now? Yeah, it is possible. So, its resonating structure will be like this: CH2 negative, CH, double bond C, H and H, and one hydrogen is here. So, negative charge or pi bond will be delocalized. Now, how many hydrogen are there? Three hydrogen are there. So we can form three hyperconjugative structure of this alkene. So basically, hyperconjugation is that type of conjugation in which one pi bond and other sigma bond take part. In this case, in pure conjugation, there was only pi electron, but in hyperconjugation, we have pi bond as well as CH bond of carbon. Now, in hyperconjugation, as you can see, these type of H are important. So this carbon is known as, this is alkene, and this carbon is known as alpha carbon. So how many alpha hydrogen are there? Three. So how many hyperconjugative structure are possible? Three. Similarly, if we take another example of carbocation, CH3, CH positive, and CH3. Now, which electron will take place or which hyperconjugation will take part? Let's have a look. CH3, CH plus, and I have broken this bond of carbon. So now I have again 6 cases of resonance, which we have discussed in the last lesson. That is positive charge and no lone pair on same adjacent carbon. How many again? In this case, tell me the number of hyperconjugative structure which are possible. Hyperconjugative structure. See, this is the main functional group in this case. So this is alpha carbon, this is alpha carbon. So how many hydrogen are there? 6. Hydrogens are there 6. So how many hyperconjugative structure will be there? 6. So in the first case, 3 hyperconjugative structure were formed. In this case, 6 hyperconjugative structure will form. So technically, remember this: hyperconjugation is proportional to number of alpha hydrogen. More is the number of alpha hydrogen, more will be the extent of hyperconjugation. One very important aspect of the hyperconjugation is where it is applicable. Like I effect is applicable everywhere. M effect is applicable when there is resonance, but hyperconjugation is applicable only in 4 cases. So what are those 4 cases? First, stability of alkene, which we won't need much stability of alkene. Second is stability of carbocation. For IB purpose, this is important, like which carbocation is stable. Then third, stability of carbon free radical. Stability of carbon free radical. So in reaction, when we have intermediate like free radical and carbocation, we will need this order. Fourth is alkyl group attached to benzene ring. These are the four cases in which hyperconjugation will be applicable. So let's take an example how hyperconjugation works. So technically, this is what I will need. Compare the stability of carbocation. We have these carbocation CH3, C plus, CH3, and CH3. This carbocation is known as 3 degree or tertiary because the carbon with positive charge is attached to 3 carbons. Similarly, the another one I will draw 2 degree CH3, CH plus, and CH3. This is 2 degree or secondary. Then we have this is primary and this is methyl carbocation. So we have to compare their stability. Now let's calculate the number of alpha hydrogen in all these structures. How many alpha hydrogen can you see here? Alpha hydrogen 9. This is the carbocation. So these three carbon are attached to it. 3 plus 3 plus 3 alpha hydrogen is 9. Now in this case alpha hydrogen is 6. In this case it is 3 and in this case it is 0. So this is the stability order which you have to remember. 3 degree carbocation is more stable than 2 degree, which in turn is more stable than 1 degree, and which in turn is more stable than methyl carbocation. This is known as methyl carbocation. This order we will need in two or three types of reaction in IB. So this order is very important. Hyperconjugation is directly not included in our syllabus, but the effect or the application is we need. So it is important here. So we will do this hyperconjugation. Similarly, we can compare the stability of free radical. If I ask you guys, what is the stability of free radical? So it is a 3 degree free radical. Then we have 2 degree. Then we have 1 degree, and then we have methyl. Remember, hyperconjugation always stabilizes, but it's not applicable everywhere. So when it is applicable, it will stabilize. So what is the stability order in this case also? Same order will be there. So remember, 3 degree free radical is stable than 2 degree, in stable than 1 degree, and it is stable than a methyl. So this order we will need later on when we will do substitution reaction as well as electrophilic addition reaction. Okay, so this is hyperconjugation and it is used in these cases. Now we will move ahead, and before starting the electrophile and nucleophile part, there is one last thing which we will do, that is aromaticity. The question is why benzene is so much stable. Although benzene has three pi bonds, but still it is highly stable. So aromaticity is not directly involved, but it is important to understand the basic of organic chemistry. Let's talk about aromaticity. What is aromaticity? See, it is defined by Huckel rule. So aromaticity is a collection of two or three conditions. If a compound satisfies those conditions, it is highly stable. Now, what are the conditions for aromaticity? First condition, cyclic planar molecule. It is applicable only for cyclic compounds and planar. That means each atom should have the hybridization sp2. Second is conjugation in whole ring. Each atom of the cyclic ring must be involved in conjugation. And the third condition, which is a bit important, is 4n plus 2 pi electron and n belongs to whole number. So which pi electron? Let's start. Let's put n equal to 0. So how many pi electron? 2. Then 1. 6 pi electron. That's more than sufficient. So if these conditions are satisfied, a compound is known as aromatic. What is the benefit of aromaticity? it is highly stable. So it's more stable than resonance actually. So let's talk about benzene and let's apply this condition and see if benzene is aromatic or not. Okay. So we have a benzene ring with three conjugated pi bonds into it. So let's check the stability. Is the molecule cycle? Let's calculate the hybridization of each carbon. Yeah, each carbon is sp2, 3 sigma bond are there. So each carbon is sp2 hybridized. So it's a planar molecule. So there is no issues in the first condition. Let's talk about the second condition, conjugate. Pi, sigma, pi, sigma, pi, sigma, pi. So the whole ring is conjugated. All the atoms in the ring are conjugated. So the first two conditions are checked. Now let's talk about pi electron. How many pi bonds are there in conjugation? Three. And how many electrons are there in one bond? Two. Two electrons are there in one bond. So 3 into 2, how many pi electrons are there? 6. So all the conditions are satisfied. So benzene is aromatic. Okay. So now what is the benefit of this? Benzene is highly stable. It Okay, we know that for unsaturation from our IGCSE and lower classes, we know that uh, bromine water test is used for unsaturation. But benzene, although having three pi bonds, it won't be giving the unsaturation test. It won't be reacting with bromine water. So that is the stability of these pi bonds. It won't be showing any electrophilic addition reaction, although it has three pi bonds. So which is more reactive for electrophilic addition reaction? Benzene or alkene? Reactive, more reactive. Alkene, and more stable is benzene. So this is what you have to remember from the nature of aromaticity. Now, a bit extra knowledge is also there. That is, if a molecule satisfy condition 1 and 2, it's and have condition 1 and 2, and it has 1 and 2, and it has 4 n pi electron, like 4 pi, 8 pi electron, then it is anti-aromatic. And if a molecule does not satisfy at least one out of first two condition, it's non-aromatic. You don't have to remember the conditions, but you have to remember this order. I mean, in order to understand the mechanism of reactions of benzene, we will need this order, stability order. So the most stable as it should be is aromatic, then non-aromatic, and then it will be anti-aromatic. So what do you think? Which compound will benzene go from aromatic to non-aromatic or anti-aromatic? No, because it is highly stable while being aromatic. Comparison of all effects. Okay. So as we have seen, there was transfer of electron in resonance. So the strongest effect out of these is M effect, which is due to resonance. That is, resonance has the maximum impact. Then we have hyperconjugation, and the least impact is of inductive effect or I effect because it was just mere shifting of electrons. So this is the effect. So let's put this effect into use and let's solve some questions. So the first question is you have to compare the stability. Okay. CH3, CH plus CH3. Then this is benzyl carbocation. Its name is benzyl. Benzyl. Okay. Third, CH2, double bond CH, CH2 positive. And the fourth one is CH3, CH2 positive. You have to compare the stability of these carbocation. Do it. Order. Now, in the first effect, there is no conjugation where there are six alpha hydrogen. In the second, there is a resonance in the whole ring, that is three conjugated structure will be formed. In the fourth one, there is one resonating structure. In the fifth one, there are three alpha hydrogen. So the highest stability is for second, then for third, then for one, and then for four. So this is what we will need in the questions. So this is how resonance, hyperconjugation, and inductive effect will work. Okay. So now we are done with the basis of these effects. Next, we will move to isomerism. And after isomerism, we will start the type of reaction which we'll need, that is substitution and all that. So now we are starting with our next part, the basics of organic, which won't be directly asked in the questions, but they play a huge role in determination of answer or determination of major product. So our next topic is isomerism. So let's start with isomerism. Okay. Now, what is isomerism? Or what are isomers? Let's define them. See, isomerism. Okay, let's define isomerism. So, what are isomers? Yeah, what are isomers? Isomers are those compound having same molecular formula. No, but different physical or chemical or both properties. So they have same molecular formula, but properties are different. Now, let's talk about the types of isomerism, and then we will see different type of isomerism. So broadly, isomerism is classified into two categories. That is structural isomerism, and second is stereoisomerism. Now, what is the difference between these two? See, structural isomerism, in structural isomerism, there is difference in shape of the molecule. That means it can shift the bond. We can change the connectivity of the bonds. Bond can be broken. They can be realigned. Atoms can change their position in structural isomerism. But in stereo means 3D. We can't change the position of the atoms. That is, their connectivity should be same. So when they're arranged in 3D, then their shape will be different. Otherwise, all the structural and molecular formula will be same. So let's talk about how many types of isomerism, structural isomerism is there. We have uh, technically four types of structural isomerism, although, so let's talk about one by one. First is chain, chain isomerism. Second is position isomerism. Third is functional. Fourth is metamerism. And one more we can define as tautomerism. Although metamerism is a special type of position isomerism, while tautomerism is kind of a special type of functional isomerism. So metamerism. Metamerism. Metamers, yeah, metamers, and tautomerism. Now, what about stereoisomerism? It is of three types, but we will need only two types. It is geometrical, optical, and conforms. Now, one by one, we will talk about these isomers. So, first is we will start with structural isomerism. Okay, so let's start with structural isomerism. And the first part is chain isomerism. Now, as the name suggests, what is a chain isomerism? See, the first part will be same in the definition of all the isomers. That is, molecules having compounds having same molecular formula. But in chain isomers, what is the difference? The difference is that they have different number of carbon in their main chain or in their parent chain. That is chain isomerism. Let's take some example of chain isomerism. For example, we have one alkene like C5H12. This molecular formula represent alkanes. Now I'll draw the structure CH3, CH2, 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 and CH3. So how many carbon are there in the parent chain? Five. Now, using same formula, I am drawing this structure. How many carbon are there in the chain? Four. In the main chain, there are four carbon. So when we will write their IUPAC name, there will be change in their longest chain. The first one is N-pentane, normal pentane, and it will be 2-methyl butane. So this is the difference in chain. One more we can draw. There are four carbon in main chain. We can draw three also. So this is and this is. So it will be 2,2-dimethyl propane. So this is a chain isomerism. So in chain isomerism, the UPSC name change and the change in is it in between its parent chain or word root. So this is chain isomerism. Now let's move to the second part. Then we'll see the combined question. Second is position isomerism. Now what is position isomerism? As the name suggests, there will be a change in the position. Now change of position of which entity? It may be a functional group, it may be a branch, it may be double bond. So, how we define position isomerism is that we have same molecular formula, but the position of functional group or by double bond or a branch will be different. Let's take an example. For example, I have this compound. What is the IUPAC name of this compound? But1-ene. Now, I'm changing the position of pi bond here. So, what is the next compound name? But2-ene. So, one thing that is important is there shouldn't be any difference in the chain, carbon in chain. There shouldn't be any chain isomerism, and then we will define the position. For example, let me take one more example. CH3, CH2, CH2OH, CH3, CHOH, CH3. This is propane 1 ol, and this is propane 2 ol. So there is a change in the position. So that's why they are named as position isomers. Okay, so let's solve one question on this. Draw all isomers, all structural isomers, not all isomers, all structural isomers that is chain and position of C6H14. Yeah, do it. 5 minutes. See how to draw. We have first draw 6 carbon in a chain. Okay. Now this is an hexane, normal hexane. Now we will draw its next isomer, chain isomer, that is 5. So I'll draw like this. There are 5 carbon. Hydrogen we can fill later on. No problem with that. Now, how many branches are there? We have drawn 5 carbon in a chain. Now, there is one branch which is to be attached with this, right? Now, I'm giving you a simple concept of symmetry. See, can you see this molecule has a symmetry on this carbon? What does this symmetry means? It means that if I attach branch to this carbon or this carbon, it will form the same compound. Similarly, if I attach carbon to this or this, it will form the same compound. So it avoids the duplicacy. Okay, let's attach the branch. We know that we can't attach the branch to the first and the terminal carbon. So there is one position which we can attach the branch, that is this one. In another case, I can attach the branch to this carbon also. So now this has concluded. So we have got 2 position and 1 chain isomers. Let's move ahead now to the 4 chain with 4 carbon. Okay. How many branches we have still have? 2. Now what is the symmetry? Where is the symmetry? This is the symmetry. So this and this are same, but we can't attach to the branch to the first and the last carbon. So we can attach either to this or either to this. So let's attach the branches. So what we will get is C, C, one branch here and one branch here and here and here. Got it. So this is technically we have uh, this compound. Now, one more case when we have branches on different carbon. We have 2 branches, so we can attach different carbon like this and this. So this is total 5 isomers which are possible for C6H14, and you have to remember it. It will used in other questions. Okay. So this is the chain isomers and position isomers. Now we are moving to our next, that is functional isomers. Okay. So